Hello everybody, welcome back to Calculus 3 Online at Frederick Community College. In this video we will discuss section 6.5 Divergence and Curl. As the title suggests, the main focus for this lecture is to discuss divergence and curl, so we will talk about the definition, how to compute them, and what do divergence and curl tell us about a given vector field. The first thing that we will discuss is divergence. You can think about divergence as the behavior of a vector field towards or away from a point. Here you see the definition of divergence. If we have a vector field F with components P, Q, and R, such that the partial derivatives exist, then the divergence of F is defined by the following formula. We will use div for the notation, and then we take partial derivatives of the components and add them up. So p with respect to x plus q with respect to y plus r with respect to z. Okay, and here is just another notation for the same function, and we get a scalar function. Okay, so notice what happens. We take a vector field, we compute its partial derivatives of the components with respect to the corresponding component, and then we add them up. So we get some function, let's say little f, of x, y, z, not a vector field, a scalar function. Okay, so let's take a look at a couple of examples of vector fields in R2, which are easier to visualize. So it will make sense as far as the behavior of a vector field towards or away from a point. So let's take a look at the first example. Here we have a vector field F that's defined by this, negative y for the first component, x for the second. And once we compute divergence of this vector field, very simple computation, we get 0. So what does that look like pictorially? Well, let's just pick a point in R2, any point, let's say something over here. And then if you look at the behavior of the vector field, the same amount of the vector field is flowing in as flowing out. Okay, and it is the same for any point that you pick in the plane. Okay, so we would expect for a vector field like this, the divergence to be 0. And it is. Okay, it's easy to compute and verify that. Now, in contrast, let's take a look at a vector field that looks like this. So here we have a vector field F that's defined by negative x for the first component, negative y for the second component. And the divergence here is negative 2. So while it is constant, it is not 0. Okay, and if you pick a point, let's say a point over here, okay, there's a lot more stuff flowing in, okay, a lot more vector field flowing in than flowing out. Okay, and you can pick any other point and see that visually that that's what's happening. So it makes sense that for this vector field, the divergence would be negative. All right, and in this class, in this video, we will discuss divergence of vector fields in R3, but I just use these examples to demonstrate this property, this behavior of a vector field away or towards the point. Let's discuss some examples of divergence and also some of its properties. You can think about divergence as measure of expansion, contraction of a vector field at a point. And once we compute this function, if divergence is always positive, we say that the vector field acts as a source. If the divergence is negative, we say that the vector field acts as a sink, and you can refer to the picture of the vector field in example 2, when divergence was always negative 2. So you can think about that flow that was going towards the origin, right? So that's the visual representation of a vector field acting as a sink. Now, if the divergence is 0 for all points in the domain, we say that vector field is source-free, and we will discuss this type of vector field in a little bit more detail. So now let's take a look at some examples. Here is the first example where we would like to compute the divergence of this vector field 12x minus 6y minus 6z. So we take the partial with respect to x of the first component and add the partial with respect to y of the second component and add the partial with respect to z of the third component. And the computation is pretty straightforward. We get 0, so this vector field is source-free. Okay. Let's take a look at the second example. Here is another vector field in R3 with components x squared yz, negative xy squared z, negative xyz squared. Okay, so similarly, we compute the partials. Okay, here they are. We add them up, and in this case, we get a function that is not a constant function. It is not 0, negative 2xyz. So for some points, the divergence will be 0, right? If either one of the coordinates of the point is 0, then the divergence at that point will be 0. But we can also get negative numbers, positive numbers for the divergence, very large numbers, and very small numbers. Okay, so it all depends on which point that we're computing divergence for. All right, so this vector field is not source-free. And let's take a look at one more example. So here is my third vector field with components e to the power negative x plus y, and then e to the power negative y plus z, and e to the power negative z plus x. So these are the components of our vector field. So same as before, we compute partials of each of the component with respect to the corresponding variable. Okay, we add them up, and now let's analyze this function a little bit. If I factor the negative, then inside the parentheses, I get an expression in terms of e. And no matter what the point is, right, what are the coordinates of point is, so x, y, and z, if I plug in any values for x, y, and z, the expression inside the parentheses will always be positive. But the negative on the outside will make it negative. So this is an example where the divergence is always negative. Okay, so this is a vector field that acts as a sink. Okay, so here you've seen a couple of examples of divergence of a vector field in R3. Okay, fairly straightforward. I wanted to emphasize once again that once we compute it, we get a function, a scalar function of 3 variables. Let's take a look at our next concept for today's class, and that is curl. Curl is a measure of rotation of a vector field about a point, and here is the definition of it. So we say if we have a vector field in R3, then curl is a vector quantity. Let me go ahead and put an arrow on top of this. So curl of vector field is defined as the determinant of the following matrix. So we set up I, j, and k on the first row of the matrix. On the second row, we put our operators, partial derivatives, d dx, d dy, d dz. Okay, and on the third row, we put components of the vector field. All right, and notice what the outcome will be. The outcome is another vector field. Okay, so while divergence is a scalar function, Curl of a vector field is a vector function. Okay, and it's also defined as the following. So this is the cross product of the gradient operator and the vector field itself. Okay, a couple of properties that we can discuss briefly. So if we have f as a scalar function with continuous second partial derivatives, then once we compute the gradient, so this is right here is the gradient of f, and then we compute curl of the gradient. So this is what it's saying. Curl of the gradient of a function f is the zero vector, which means that this vector field, the gradient field, is irrotational. Okay, and then we say that if a vector field f, whose components have continuous partial derivative, has the property so that the curl is the zero vector, then f is conservative. So these two properties kind of go hand in hand together. All right, so now let's go ahead and apply this definition to determine if a vector field is conservative. Okay, so use curl to determine whether a vector field is conservative, and the vector field is given to us here, xy for the first component, yz for the second component, xz for the third. So if you recall from our previous sections, we have a test that tells us how to determine if a vector field is conservative. Now what we're doing here is not fundamentally any different. We're just computing this vector field, and we're going to see if we get the zero vector. But in reality, we're computing exactly the same quantities. So let's take a look at the solution here. What am I doing? I am setting up my matrix where the top row is just these vector components, right? I, j, and k. And then the second row, partial derivatives operators. Okay, so ddx, ddy, ddz, we put them in that order. And then on the bottom row, I put the components of the vector field. So xy over here, yz, and then xz. Okay, and now we compute the cross product or the determinant of this matrix. So we've done that many times. So let's see how we do this. So what is the I component? Okay, let me remind you. Then we'll look at this matrix right here. So it is the partial of xz with respect to y minus the partial of yz with respect to z. Okay. And so we compute that one, and we get 0 minus y. Then for the second component, don't forget the negative. So I put that negative here, j times what? So what are we looking at here? So that would be partial of xz with respect to x minus partial of xy with respect to z. Okay, and that gives us, inside the parentheses, that gives us z, and then don't forget about the negative, right? And then plus what? What do we have for the last one? So this is k, and we're looking at this matrix right here. So partial of yz with respect to x minus partial of xy with respect to y. Okay, so we get negative x, and we have this vector right here. Okay, negative y, negative z, negative x. You can think about this as a vector field that is not identically equal to the zero vector. Okay, notice this is not a scalar function. This is a vector function. All right, so the vector field f is not conservative. Okay, and if you go back to the section where we discussed the test for conservative vector fields, you will notice that we're doing exactly the same type of computation, except now we are looking at it from a slightly different angle, right? So we're looking at it, okay, if all of those equations were true, right? All of those quantities were equal to each other. That's equivalent to saying that their difference is equal to 0. Okay, so F is not conservative, so that is one other way to check whether the vector field is conservative. Let's discuss a couple more examples of computing the curl. Okay, so here is my vector field F1 with components x squared minus y squared, x, y, and z. Okay, so let's go through the computation here. Curl of this vector field is the determinant of the following matrix. So we have I, J, K on the top row. And then on the second row, we have partial derivative operators. And now I just copy my components. So x squared minus y squared, x, y, and z. Okay, carefully compute the determinant of this vector field. So the first component I, okay, again, let me show you how we do this. Just a quick reminder, we'll look at the determinant of this matrix here. So this would be d dy of z minus d dz of xy, okay, and that is 0. All right, then the next step is to take a look at j components. Okay, I don't forget my negative sign over here, so that would be d dx of z, which is 0, minus d dz of x squared minus y squared, that is also 0. So the second component of the curl is also 0. And then what about the last step? So for third component, d dx of xy, okay, minus d dy of x squared minus y squared. So here we do not get 0. So we get a vector field of the following form: 0 for the first component, 0 for the second component. Third component is non-zero. It is 3y. Okay, so this vector field is not conservative. It is also not irrotational. Okay, one more example. We're just going to take a look at the answer. All right, so here you have this vector field with components x squared minus z squared, 1 and 2xz. And I'm giving you the setup, and I'm going to let you check the work. Okay, so pause the video, see if you can work out the steps here, and see that you get exactly the same thing as I do. So the vector field produces the following curl: 0 for the first component, negative 4z for the second, 0 for the third. Okay, so this is not identically equal to the 0 vector. Okay, so this vector field is also not conservative. It is not irrotational. So now that we have discussed the main concepts of this chapter, chapter 6, I'd like to give you a quick summary of the main ideas. And I'm not going to take credit for this. I've seen this type of summary in several textbooks that I used to supplement this class, but I thought I would share some of the notes with you to kind of help you summarize everything and organize it really well. So the first thing that I want to talk about is vector fields that are conservative compared to vector fields that are source-free. So let's say we have a vector field in R2, F, with components little f and little g. Then we can take a look at two different types of vector fields: conservative vector fields, and we know a lot about those. We've discussed these type of fields in detail. And now in this lecture, we introduced another type of a vector field, and that's source-free. So the definition, right? What is the definition for these vector fields? We say that the conservative vector fields are those where we have a potential function, right? So we have a potential function phi, so that the first component of the vector field is the first derivative with respect to x. The second component of the vector field is the first derivative with respect to y. So we know that, okay? And now I'm going to just briefly introduce stream function. The Greek letter for it is psi. Okay, the stream function is defined like this. The first derivative with respect to y of this function is the first component of our vector field, and negative of the first derivative with respect to x is going to be the second component. Now, you haven't missed anything. We haven't really discussed this function at all, but I thought I would mention it at least in case you encounter something like this in your physics class. Okay, so this goes for what? So stream functions are kind of like an analogy of a potential function for conservative vector fields. Stream functions go with vector fields that are source free. Okay, and what can we say about conservative vector fields? Those are the fields where curl is equal to 0. Okay, and source free vector fields are those where divergence is equal to 0. What else can we say? For the conservative vector fields, whenever we have a line integral over a closed curve, okay, notice notation here, closed curve, then the circulation, which is just the line integral over that curve, will be 0. Okay, similarly, for vector fields that are source free, line integrals over closed curves are 0. Okay, and if we are working with curves that are not necessarily closed, so here C represents just an arbitrary curve. Okay, we have a computation here that this is line integral of a conservative vector field, right? So we would apply fundamental theorem of line integrals. Okay, the computation becomes phi of b minus phi of a. Okay, just a quick reminder that that's what we would apply here. And then similarly, we have a formula over here where we would say psi of b minus psi of a. Again, I want to emphasize we did not discuss too much of source-free vector fields. You haven't missed anything. This is the first time I'm mentioning it, and I wanted you to know in case you will need this in your physics class. Okay, so that's your first summary for vector fields in R2, and you can hopefully see a little bit of a similarity here in this table. Now let's take a look at another summary here. So if we look at circulation or work integrals, okay, we can kind of split it up into several categories. So for the curves can be either closed or not closed, okay? And for the vector field, we also have two types, conservative and not conservative, okay? So now you can follow this table and say, if I have a vector field that is conservative and I would like to compute the integral over a closed curve, then the line integral of this type will always be 0, and that is something I raised in one of my lectures. That was a question that I posted, and I asked you to send me a message if you thought about it and you came up with a solution, and some of you did. Okay, so there is the statement here. If we have a vector field that's conservative, the line integral of that vector field over a closed curve is 0. Now, if it is not a closed curve, that's fine, no problem here. We still can compute that quantity, so that would be phi of b minus phi of a, where a and b are endpoints of the curve, right? So a is the starting point, b is the terminal point. All right, and then if a vector field is not conservative, but the curve is closed, then we apply Green's theorem. Okay, so here's your application here. Now, if the answer is no to both categories, it is not closed, it is not vector it is not a conservative vector field, then we just do direct evaluation, and that's what we've done at the very beginning of this chapter. Okay, so I believe that was section 6.2, right? So we can still compute line integrals of any vector field over any piecewise smooth curve. Okay, we just have to do the direct evaluation. So here is another table we can come up with for flux integrals. Okay, another type of line integrals. Same idea. We split up our curves into either closed or not closed. Our vector field now, source-free or not source-free. Okay, and what happens here? If the answer is yes to both, it is a source-free vector field and the curve is closed. Once again, we get the line integral over that curve is 0. Okay, if it is not closed but the vector field is source-free, we get the following evaluation. We haven't done that, okay? You haven't missed anything, but I wanted you to see that comparison, okay? And then if the answer is no, not a source-free vector field, but it is over closed curve, then we apply the flux form of Green's theorem. Okay, we've done that. And then if the answer is no to both questions, not source free, not closed curve, what do we do? And direct evaluation, we also have done that at the beginning of chapter 6. Okay, so these tables right here might be helpful for you to kind of organize all of these concepts and put them in order, because there's a lot of terminology in this last chapter of the course. So sometimes we may get lost in the notation and terminology, trying to figure out what's going on and how to approach a problem. So I would recommend copying these tables, really going through it, thinking about it. When did we make this connection? Not just looking at as a bunch of formulas, but really trying to understand the connections between these quantities, such as curl and divergence, flux and circulation, and so forth. Okay, so I hope you find these summaries helpful in organizing all of this material that we've covered in the last few weeks. So divergence and curl of a three-dimensional vector field is the last topic in our class. This is a nice place to stop, as it sets up a stage for the 3 topics that we are not going to cover in this class. Okay, surface integrals, Stokes theorem, and divergence theorem. These are extensions of the results that we've already discussed in our previous lectures, but they do become a little bit more technical, more involved, heavier in computations, and somewhat challenging to visualize even with the technology that we have. So I prefer to stop right here. Okay, I hope you enjoyed the class. I hope you realize just how much you've learned, starting at pre-calculus, going through analyzing all the various functions such as polynomials, rational functions, logarithmic, exponentials, and trig. So you've talked about all of those. Then you talked about calculus 1, where you learned about limits, derivatives, antiderivatives, looked at some applications of calculus, okay, and then you also took calculus 2, where you've discussed all sorts of methods of integration and applications of antiderivatives, and now you've completed the entire sequence. Okay, so we are at the grand finale of calculus 3, so congratulations everybody. It is an incredible achievement. You should be very proud of what you've done, how much you've learned, and how much you've matured mathematically. I hope you enjoyed taking this class. Thank you all for watching all the videos, for doing all the work, completing all the assignments, and I wish you best of luck in all of your studies. Thank you.